So my name is Aseem Kishore. Thank you for coming. I'm a developer at a startup in New York called FiftyThree. We make an iOS app called Paper. For some reason, this is getting clipped off on the stage, so don't worry about it. But hopefully, you've already heard of us, and maybe you're using us today for the conference to capture your notes. But if you haven't heard of us, I'll just the only thing I'll say about Paper is this 1 minute. I'll talk over it if that's cool. Basically, with Paper, the purpose of the app is to let you capture your ideas as quickly and efficiently and beautifully as possible. And ideas come in many shapes and forms, right? They come as text sometimes, as lists, as checklists that you can drag and drop. No more having to select text and cut and paste. We have this thing called swipe to style, so you can indent lists just with a swipe, right? Sometimes ideas come in the form of photos. So at a conference, I hope you guys use your phone to take photos of this talk, various slides. And sometimes you want to annotate those photos. You might want to circle something, or you might just want to draw out a sketch. Maybe it's a graph data model, maybe it's something else. So we make tools to let you do that as beautifully and efficiently as possible. And we're really excited about it. So we're on iPhone, we're on iPad. I hope you guys will try us out if you have those devices. Paper also has a major social and collaborative layer. So we have a service in the cloud to let you share your ideas and follow other people and remix other people's ideas. We're doing more work there, but that service is powered entirely by Neo4j. So we've learned a lot over time. And I've given actually 2 other talks at previous GraphConnects, as we've kind of grown with Neo4j. And in each of those talks, I really like to focus on things that aren't obvious, things that I'm not seeing covered in blog posts and tutorials and other talks. And this talk's no different. I put advanced in the title here because unlike a lot of the previous stuff that I've talked about, the content that I'm going to talk about today, it's not stuff that I discovered on my own. I really learned it through my excellent colleagues, 2 of whom are here today, Ryan and Matt, who brought with them a wealth of experience from other databases. And so the concepts might not be new to you if you've worked with other databases, but certainly I'm not hearing this stuff talked about in the Neo4j community, so I'm hoping this will be helpful and educational. So the 2 things I'm going to talk about are actually really basic. Reading and writing is what you have to do with databases. But it turns out when you really dive into the subtleties, there's a lot there that you might be taking for granted that maybe you shouldn't be. So with reading, consistency is a really important aspect to your data. And if you're running Neo4j at a high scale, you're running the cluster, and there's going to be issues there that we'll talk about. And then with writing, atomicity is another really important fundamental principle that it turns out there's a lot of subtleties to that you might not be aware of. We certainly weren't. OK, so let's start with reading. By the way, 40 minutes is not a lot of time, so I'm going to really breeze through this. And I think the writing section is even more interesting and less talked about. So bear with me if I go a little fast. These slides will all be available online afterwards. So really quick, props to Matt and our other colleague who's in New York, Dave. They really led the charge on a lot of this stuff. OK, so here is what a typical Neo4j cluster setup might look like. By the way, this diagram was made with Paper. One of the features we have is basically you can think of it like autocorrect for shapes. So you can draw something that looks like a square and will automatically make it a nice square. And you can drag and drop those things around. So I really encourage you to check it out. But so here's a typical cluster. You have a master and 2 slaves. They're talking to each other. And then the recommended setup is to have a load balancer in front, typically HA proxy or something like that, that the clients talk to. And the other recommended setup here is that instead of sending all the traffic to a single instance or load balancing it arbitrarily, to have 2 separate pools. One pool will send requests to the master, and the other pool will send requests to the slaves. And because Neo4j is a master-slave setup, the typical recommendation for how you split these pools is reads versus writes. For a lot of applications like ours, reads vastly outnumber writes, and so being able to horizontally scale reads is obviously very effective and very valuable. But one thing that we've learned at FiftyThree is and I will contend that that's not the best way to split your traffic. You should really be splitting it by the consistency that you want. So writes are obviously always strong consistency, and reads often can be weak consistency, but we've discovered that there's actually a fair number of times where you want the reads to also be strong consistency. And in that case, you might want to send them to the master. So what are some examples? So with paper, I mentioned we have a whole social layer, so we obviously have accounts, and we persist those accounts in Neo4j. So we, back in the day when we used to split based on reads versus writes, we started seeing these transient errors that we couldn't repro where someone would create an account, and then the very next thing, they'd automatically get logged out. And we were trying to understand, why is this happening? And it's because our client app had code in place that if any request failed for an authentication-related reason, it would assume that either the password had changed or maybe the account had been deleted or something like that, so it would log you out. And it turns out what was happening was the write request to create an account was being immediately followed by a read request for that user, which was doing an auth lookup for that user. And if that read request was going to a slave, that user may not have been synced right away. And so there was a case where we realized, like, hey, right after sign up, we should actually be sending your very next read or reads to the master to ensure that this new account is there and up to date. The same thing applies if you change your password or do a password reset or change your email address, these sorts of things. Another good example is if you follow a profile in paper and you hit the close button, now you're back at your home stream, and paper will do a refresh of the home stream, you should see that account's content in your home stream. And so again, if a slave hasn't gotten this newly created follow relationship, and you do this home stream query on a slave, you're not going to get that content. So we were able to kind of look at all these cases, and we saw a pattern, which was, if I do an action, the very next read that I do, I should see the effects of my action. If you do an action, I don't need to see the effects of that action right away because I'm not aware that you did that action. So we arrived at this notion, internally we refer to as per user read after write consistency, which means for me, if I just did a write, my immediately subsequent reads should be strongly consistent. And so the way we achieved that, we did a little bit of research. We didn't really see how other people were tackling this problem. The way we figured we'd do it is we just simply track the last timestamp that you did a write, and we fetch that data as part of our auth lookup. And so we can see that if you just very recently did a write, we should make your read, even if this API request is a read request, we should make the read request to the master for strong consistency. Like I said, I'm going to breeze through this. Don't worry too much about the code. This will all be online. I mentioned we do this as part of auth lookups, so that obviously implies that the auth lookup should be strongly consistent also. And so that's something we do. Here's a little code sample where all our auth lookups are sent to the master, but then after that, we might send queries to slaves if the queries are read requests and we don't need them to be strong consistency. This does mean that all of our auth lookup reads are going to the master, which does not horizontally scale. That hasn't been an issue for us so far because these auth lookups are very fast, very simple queries. But we've talked about if that becomes an issue, we know we can offload our accounts. We can remove them, instead of being in a master-slave system like Neo4j, we can move them to a horizontally scalable system or cache them in Redis or something like that. So now going back to the question of how recently did you do a write? Well, how do we define recently? What should the threshold be? That's not an easy question to answer. That's a question that even today I wouldn't say we feel confident in our answer for, but we have a sense for how to arrive at it. So ultimately what it boils down to is the slave lag. How far behind are the slaves relative to the master? And how long does it take them to catch up and all that stuff? So it's possible to monitor this stuff in Neo4j. It's not necessarily easy today, but they're aware and they're working on it. But thanks to Matt and Dave, we have some tooling where we can look at the last committed transaction ID per instance. We know which instances are the master and which ones are the slaves. And so what we do right now, we just sample that data every 15 minutes and just send it to a Slack channel, just so we kind of get a finger on the pulse and get a sense. Don't worry about these specific numbers, but suffice to say that what we see today is thankfully the slave lag is pretty minimal, with relative to the raw rate of transactions that are going through the system. So that's definitely a factor in all this. The other major factor in all this is the various HA configs, and pull interval is probably the most important one. Push factor and push strategy are the other important ones. I think Ian Robinson has talked about some of these. What I pasted here, by the way, is the default snippet, and I want to say that the default snippet isn't necessarily the optimal snippet for you. It wasn't for us. We were actually living with this for, I want to say, like a year or more, until more recently we revisited this with Neo4j support, and we realized like we can actually do a lot better. So the default snippet has the pull interval, meaning how often slaves are querying the master, at 10 seconds. And today we have set that to 500 milliseconds. So given that, this 500 millisecond amount with the lack of significant slave lag we're seeing, we have set our read after write consistency threshold at 2 seconds, meaning that if you do a write, then for the next 2 seconds, all your read queries will go to the master. And so far, that's been working well for us, but that's something that we can still play with and tune. There's also a more subtle consistency that could come into play, which is read after read consistency. And what that means is if you have 2 or more slaves, as you should, if one read query goes to slave A, and then your subsequent read query goes to slave B, and they're not in sync, you might get a consistency flapping. Like a user might see, hey, this photo exists for 1 second, and then the next second it doesn't exist. So thankfully, we haven't felt this issue ourselves, and you can see why, because the slave lag is so minimal. But if that's something that crops up for you, one way to solve that, which we've talked about, would be to simply use DB, like instance stickiness per user. So that means, for example, in the HA proxy config, you could say that you could have your app code send the user ID as a header, and then in the HA proxy config say, always route this header, particular value of this header to the same slave. So I know I went through that pretty quickly, but some of the takeaways of that are, split on consistency, but be robust to read after write and read after read consistency. And both of those are, really determined by slave lag, which is not a simple thing to monitor, but you should be aware of it. And, if you're an enterprise customer, talk to support about it. Great. Okay, so now I want to get to the right part of this talk, which I think is a lot more meaty and a lot more interesting. And for this, I want to give props to my colleague Ryan. He's really the one that discovered a lot of the issues here and really made our systems much more robust. So for this context, I mentioned the paper has a social layer. So part of that, like I mentioned, is that users can follow the users. So let's just focus on that part of our graph. We have a lot of other stuff going on, but just that. So 2 aspects. So one is I want to be able to follow someone and unfollow them. And the other is we cache some stats for performance. Just like Twitter will show you the number of followers and number of following for a user, and it should be able to do that without actually fetching that list. We want to do the same thing, so we cache a numFollowers property and a numFollowing property per user. So what that means is every time I follow someone, I want to increment the right properties, and every time I unfollow someone, I want to decrement the right properties. So let's look at just the simple increment case. Very simple line of cipher. Does it do what you think it will do? And if I'm asking that question, the answer is probably no. If you've ever done multi-threaded programming in any language of your choice, you will recognize this classic C equals C+1 case. And the reason it's a classic case is because it's susceptible to a race condition where you're doing a read before a write, and so if 2 parallel actors are doing the same call, it's great if that happens in sequence, but if it doesn't happen in sequence, if both actors do the read before either one has done the write, then they're going to both write the same value rather than building off of each other. So that's, like I said, that's not new to anybody, but it's good to know that that's in fact, the case with Cypher, with Neo4j. And this boils down to the specifics of what the I in ACID stands for and what, how you implement it. So the Neo4j manual is actually pretty explicit and straightforward with this, that Neo4j uses a read committed isolation level, it's called, which means that reads are not protected from concurrent modifications by other transactions. And in particular, only write locks are taken. And so what that translates to, if we go back to this read, increment, write flow of steps for that line of Cypher, that whole series of steps is the transaction, but a lock is only taken at that last step. And so again, if we go back to the race condition, it makes sense because the locks are only held for the write, and it doesn't actually prevent the reads from happening out of order. So, so the good news is, while this is the default behavior, the Neo4j manual and the Neo4j team argues that it's actually a good default. It offers significant performance advantages. And the even better news is you can work around it to achieve higher levels of isolation, namely serialization, if you want to and need to for your use case. We do. And so the way that works basically is instead of, I'm just going to take out the increment, by the way, from this diagram because it doesn't really play a role here. It doesn't change the semantics. So we're going to remove the increment, and then we're going to add a write before the read. And so if we can do that, then we can acquire the write lock that we want, and now our entire transaction is serialized if there's multiple actors. So if we change that, even if both transactions occur, begin at the same time, only one will get the lock, and the other one will have to wait and wait and wait until the first transaction finishes, and that guarantees the serialization, the sequencing that you need to prevent this race condition. So that sounds good, but how do we actually do that in Cypher? Well, it turns out that the manual just, explains this a bit more too. So a couple important points. So locks are required at the node and relationship level. And specifically, when you modify any property, and modify here means creating a property, deleting a property, changing a property, a lock is taken on the entity that that property belongs to. So if you want to acquire a lock on a node, all you have to do is set any property on that node. And it can be any property to any value. What I'm showing here is the convention that we use in our own Cypher queries. This underscore lock property doesn't have any semantic. The true doesn't matter. It could be a string. It could be a number, whatever. But it's just the convention we use so that we can see our locking in our queries the same way in every query. So if you write your query like this, then you can nicely take the write lock and prevent that race condition. But obviously, you need a node in the first place. So in our case, let's say we match on a, we do a match clause to get the user whose property we want to increment. But now the problem is, you'll notice that we have a user label. What happens if there's another concurrent query that removes that user label? And in case that sounds far-fetched to you, this is actually something we do in practice. We implement kind of partial soft deletes so that we still retain some history for our deleted nodes. And the way we do that, in order to not break all the queries that perform indexing lookups and all that stuff, is to just change labels. So we swap out a user label for a deleted user label. So now what happens if this first query finds a user, and then a second query right there swaps that user label for a deleted label out? Now we're going to execute our first query even though we really don't want to. So the answer here is something known as double check blocking, which is go ahead, take the write lock like we were, but then after the write lock, verify any reads that you've done previous to it that could have changed. So in this case, the part that could have changed for us is the user label. So we just verify that that user label still exists on this node before we do our write. Great, so that's all good and well for properties on single nodes, but now what about relationships? So here's a very common concept, ensuring that you have idempotent relationships. So in our case, that just means there should only be one follows relationship from me to Alice, not two. So I'm going to get to the merge keyword in a sec, but just for the sake of illustration, what this might look like is where this relationship doesn't exist, create it. So going back to how the locks work, when you create and delete relationships, a lock is taken not just on the relationship, but also the start and end node. And so that's really important, because that means if we want to ensure that we aren't susceptible to race condition, and let me back up one sec. The race condition here, let me just be explicit, is you could think that there's no relationship between me and Alice, but then a concurrent second query will add one right after that. And so then you might get two relationships, which we don't want. So the good news is we know the simple way to prevent that now is just to take an explicit lock on both the start and end nodes, and that'll ensure that once we do our read to see if whether a relationship exists, a relationship will not concurrently get added or deleted after that. Good news is the merge keyword in Cypher does do this. We weren't sure if it did at first, but just some quick testing showed that it does do this pretty robustly, so that's good. Unfortunately, merge is not a silver bullet because you typically don't want to merge your entire pattern. Notice I didn't put the user labels in my merge because I don't want to actually create users if Alice is just trying to follow Bob. I only want to merge the relationship. So I'm going to be doing a match before the merge, and so we're back in the state now where I'm doing some reads before I take any write locks, which means we need to solve it the same way, which is go ahead, do the matches, but then take the write locks explicitly and then verify the matches. So even if you're thinking, well, hey, the label thing, like, we don't swap labels out. That's not a concern for us. That's fine. There's other cases where you might encounter this. So another example of something that we actually do in practice is we want to verify that Alice hasn't blocked me if I'm trying to follow her. So our system has a notion of blocking just like Twitter and Facebook. And so here also, this check for blocks doesn't belong in the merge, and it's another example for read. So the race condition here is that I might think that there's no blocks relationship, but a second concurrent query creates one, and now my follows is illegal or invalid. So here again, the good news is we know the solution, but here again, it's just showing that you have to be very conscious of this stuff. Just think about what reads you're making before a write, and what parts of those reads could change. So now, you'll notice that with both these examples, we're taking two locks. It's technically not necessary to take two locks, right? Because creating and deleting a relationship will requires. I hope people are okay. Okay. So creating and deleting a relationship requires both locks. So taking just one lock will be sufficient, but we found that for various cases, it's actually helpful to reason about if you take both locks, because you don't want to get into a case where two separate queries are only taking one lock, and it happens to be the same lock. Sorry, I should clarify. One query is working with Alice and Bob, the other is working with Bob and Carol, and they take locks on Alice and Carol, and that might not be what you want. So you're taking two locks, and now if you've done multi-threaded programming before, you know that the moment you're dealing with more than one lock, you might be in for a world of pain. The good news is the manual also says this, that Neo4j has deadlock detection built in, so that's good. And if you've ever seen an error mentioning for SETI client, you've experienced that. And so this is the typical error you might get back if you're trying to do some concurrent operations where you're taking locks and Neo4j detects that it can't execute either one of the queries because they're both waiting for the other's locks. So notice that this error is neo.transienterror.transaction.deadlock detected. That transient error classification is really, really valuable. So in case you're not aware of this, Neo4j, and every error that it returns, it classifies those errors as either a client error, a database error, or a transient error. And that's very similar to HTTP 400 and 500, but transient error is unique. And it's funny, when I was preparing this talk, I was just doing a bit of Googling, and I came across this old GitHub comment I had left, giving the Neo4j team props for this great transient error classification. It was really smart, in my opinion. So what you can do is a client error means you have a bug. A database error means Neo4j has a bug and you should report it. A transient error means, as the manual says, you should consider retrying it. It will probably work with the retry. And so that is something that we implemented. Again, don't worry about the code. This will all be online. But at a high level, we're basically running our Cypher queries in a retry loop where if the error that we get back is a transient error, we'll do some exponential backoff and retry it. And this has been really, really valuable for us. Without a question, it has helped a lot. The good news is when you get that kind of retry architecture in place, you notice that there's a whole bunch of other things that you might want to retry on. So we, this was like half a year or more ago, we discovered at the time Neo4j had a couple of subtle bugs that weren't getting returned as transient error. And so we could easily retry on those. And then another case was there might be networking hiccups. So we run on Heroku, for instance. And occasionally, once in a blue moon, we'll see that our Heroku server isn't able to find our database. Or if there's a master failover, HA proxy might return some 502s or 503s. And so basically, we can now support all this stuff and retry on these variety of cases. And we get much better success rates, much lower error rates in the aggregate. So that's all good and fine for single queries. But if you go back to the manual, you'll notice that for each of these classifications, there's a little column that says effect on transaction. And all of them are rollback. What that means is if your query is part of a larger transaction, meaning the query is not the entire transaction in itself, it doesn't matter what kind of error you got, how far along you were in the transaction is failed. It will not succeed. The transaction will be rolled back. So what that means is you can't simply retry that individual query. You really have to retry the whole transaction. And if you're using a transaction, chances are you have some application code between the queries in that transaction. So for us, for example, one of the main places we use transactional queries is for complex deletes. Deleting a user, for instance, is not something we can trivially express in a Cypher query because there's so much recursive business logic. Like a user has a bunch of IDs that they've shared. They have a bunch of followers and following. They have backups and blah, blah, blah. And the business logic for deleting all those things is not something we could just all bunch into a single Cypher query. So that means you have to wrap your code in something that's transaction aware and then run that code in a retry loop. So again, don't worry about specific code, but at a high level, what this is showing is that we begin a transaction and then we execute our code, both queries and business logic, and we'll retry that whole thing if there's any transient errors. But if there's code in here, then you should be aware that if there's any side effects, you shouldn't be naively retrying these transactions. Thankfully, we don't have any such cases today. We might. You might, especially if you're a polyglot architecture and you have multiple data stores and you have to do a write here and then a write here. And then if this write fails, you need to make sure you roll back this other write before you retry the whole thing. Just something to be aware of. If you have side effects, don't necessarily retry. All right. There's a lot to think about. And honestly, the examples that I just showed, they're pretty simple examples of just following a single person or incrementing a single property. But obviously, in real-world queries, it becomes a lot harder to reason about what all reads are you making that inform writes, and what all parts of those reads can change, and what all locks you need to be taking. And as you take all those locks, what kind of contention do you need to be aware of seeing, and where are the bottlenecks going to be? It's hard. It's not easy. But the good news is that this is a whole spectrum of trade-offs. On one end, you can do the simplest thing and not worry about any of this stuff, and realize that some of your writes may not be fully atomic and blah blah. Maybe that's fine for your use case. On the other end of the spectrum, you could be as upfront and cautious about all this stuff as you can, and your queries will get a little bit more complex and they'll be a little bit more hard to reason about. But there's probably a good middle ground for you somewhere. For us, that middle ground is that most of our queries by default don't worry too much about this stuff. We abstract some of the key things like property increments and relationship checks into some helpers, and that abstracts away that complexity pretty well. And then we just tackle the other stuff like the double-check locking for label swaps only in the few cases where we've encountered those issues in practice. So, all this said, when I was doing this talk, I dug up a support ticket that we had going with the Neo4j team, and I dug up a couple of quotes from Ryan's response. I didn't tell him I was going to show his words here, so I hope he's okay with that. But I really agreed with the sentiment here, which was like, when we first discovered all these issues and were dealing with them, we were pretty unhappy and we were pretty it really shook our confidence. But, all that said, like, we work with the tools we have, and the good news is, like, our system is it's running very smoothly today, and we're really happy about that. Our error rate is way lower than it ever was, and we don't see any of the inconsistencies in our database that we had been seeing occasionally. So, thanks to the Neo4j support team for helping us there. I want to close by just taking what we talked about and applying it to a kind of tangential lesson. So going back to what we learned, locks are required at the node and relationship level. Here is what a typical data model you might have, and certainly it's very close to what we have, where let's say you have a user node, and over time this builds up in the amount of data and the types of data that it's storing. And so, this is a simplified example, but what I showed here is all stuff that you could imagine having a high write throughput. So we mentioned the last write tracking. We track your latest backup. We have a backup system. We mentioned the num follower stat. And you could imagine maybe you have linked lists in the graph for your home stream and your notifications and stuff like this. So all these things can have a high write throughput, particularly because most of them are affected by actions that other people are doing, not just you. So for example, if you're following 100 people, every time any one of those people posts a new idea, it's going to go to your home stream. Anytime anyone follows you or stars one of your ideas, you're going to get a notification. So that's going to change the head of your list, which is like, deleting and creating a new relationship. So what we saw was that modifying a property takes a lock at the node level. Creating and deleting relationships takes a lock at both the relationship and node level. So perhaps the lesson to be learned is that maybe instead of one monolithic node, it would be better to have separate nodes for separate concerns so that you can have more granular write throughput where someone following you is not going to contend for the same locks as you updating your latest backup. So, and the nice thing is with these nodes, they can still be linked to each other, and so you can still get all of the full picture if you need it. So this is not what we do today. We unfortunately have built up our data model with the single monolithic user, but this is something we've kind of recently started to realize and learn, and maybe if we were to start from scratch, I think we might consider this approach more. So maybe hopefully you'd find that helpful. So great. So I'm just about running out of time, so it's good. I'm amazed that this actually worked out on time. But so some of the takeaways for writes were, be cognizant of taking write locks early wherever you're doing writes that depend on reads. Verify those reads by double-check locking. If you need to do them before you can take the write lock. Realize the granularity of locks or nodes and relationships. Retry with backup on transient errors. If there's one thing you take away from this, this should be it. Retrying on transient errors is really, really helpful for us to, like I said, reduce our user-facing error rate. And based on the lock granularity, consider designing your data model with throughput in mind. All right, so that's everything. Like I said, many thanks to my colleagues. I'm really just the messenger here, but thanks to them for discovering all this stuff. And thanks for listening. All right, so I guess if anyone has any questions, Alex will be happy to pass the mic around.
Given that there's a single master in the cluster, it seems like for some of the simpler cases, like incrementing, decrementing, creating unique relationship or deleting unique relationship, Neo4j could have support for doing that atomically without requiring you to explicitly acquire locks. Have you talked to them about that kind of support?
Yes, yeah, great point. It absolutely could, and especially from a perspective of like a cipher parser and planner, it could, in theory, you know, I'm not an expert on this, but in theory it feels like it should be able to see that some part of my query is going to write property foo on node n, so maybe you could take the write lock early. That's feedback we've given to them. I know it's a hard problem for them to solve. The other approach they could take is to come up with new syntax that lets you make your intent clear at the beginning, and then maybe that query could be at a higher isolation level. So that's something that's apparently common in the SQL world. Update from where, for example, I don't have experience with that personally, but that's feedback we've given them. Hopefully it comes to fruition.
So paper app's pretty cool. I like it.
Thank you.
So I'm in the middle of building an application myself with and considering Neo4j as persistence layer for mobile application. So very relevant. How do you guys do the like API connections to the mobile application and I guess translate the graphiness to the mobile layer? And do you do persistence on the mobile client as well, or how does that work?
Great question. We do persistence that we view as caching, and it's really not trivial. We have come up with our own sort of like a graph cache algorithm where we can represent the graph as an adjacency, by the way, blah, blah. But like Netflix, Facebook, they're doing a lot of good work in this space. I'd consider checking that out. GraphQL in particular is pretty interesting. No, I haven't. Okay, thanks.
Hi. Did you end up having to develop a solution for concurrent edits? And is the latest one the one that wins, or do you try to diff them, or that kind of thing?
Yeah, great question. We haven't had to deal with that to date. We're embarking on some work that will deal with it. We're probably not going to do anything simple or naive. We're looking at operational transformation for that sort of work. For all the concurrent writes that happen today, we don't have to deal with conflicts. It's stuff like atomically incrementing a counter or properly connecting and detaching relationships, which can be serialized, and that's what we do with the write locks.
This might be a really naive question, so I apologize if it's really silly. But it seems like some of the issues with writing are because you guys have multiple concurrent writers. Have you guys considered like abstracting out the layer that writes to Neo4j and forcing writes to be done in serial?
It's a great question. Yeah, so we could use a queue for that. I know some people do that. I think for us that's not really an option because of what I mentioned earlier about like this is a user-facing app, so when they take an action, they want to see the effects of it right away. And so therefore, we need to support the writes happening right away. And in fact, like we don't return a response on the API write request until Neo4j has persisted that write. But it's a good point. If you can offload writes to a queue, then you might avoid a lot of these problems.
I may have missed this, but what do you use as the ingestion layer? Like, how do you take all the inputs?
Just with API, like a REST API.
With like Node or how?
Yeah, we're a Node.js shop.
Okay.
Okay, one more question.
Last one.
I'm not going to make fun of CoffeeScript, which is what he just asked me if I was going to ask about. No. So this is like a really appropriate place where my friend and I are just talking about graphy data versus like splitting your data stores into something that's more appropriate for, not appropriate, but maybe more scalable for like transactional stuff that you guys are doing. So I guess maybe could you talk for a few minutes about how you guys decided to use Neo4j for the actual transactional user-facing data store? as opposed to like using maybe something like Postgres or whatever you want to use. I don't care, Mongo, whatever, on the front end to like deal with user-facing data and then persisting that to Neo to do some of the graphy things. And maybe you could talk a little bit about graphiness of your data and why you need Neo.
Yeah, that's a very good question. I mean, the answer to literally your question for how we are where we are today is not any fancy answer. It's just like that's how we started as like a prototype, and it just built up. And it's obviously a lot easier to work with a single data store than multiple data stores. We're getting to the point now where we are looking seriously at extracting parts of our data into separate data stores that might suit that type of data better. So I mentioned accounts as a perfect example. Accounts by themselves are not connected data. They're very horizontally scalable, very partitionable. So moving them to even something like Dynamo instead of a relational database might be what we end up doing. And that's actually a pattern that we've seen other people do, like Medium, for instance, puts all the post content in Dynamo, and then Neo4j has all the relationships between the people that follow and recommend posts. So I think that's the way I'd view it, is like not necessarily what data is real time and not real time, but more so what data can be very partitionable and what data is very interconnected. So even if we moved accounts off, for us, Neo4j will still very much be a real-time online system because we need to be able to follow and unfollow people and connect ideas to people that remix them and blah, blah. So I don't know that you can remove Neo4j from the real-time equation if you care about the connectedness for your real-time queries. Cool. All right. Thank you very much, everyone.